You're smoking. Welcome back to Make Stuff for Fun. As always, I'm Brian. I've got some really exciting LED projects lined up. But first, I wanted to give some basic electronics background so we can all be on the same page. So today is just a very basic introduction to electronics talk. And without further ado, let's head over to the whiteboard. So we'd like to work with LEDs. Now, before we can work with LEDs, there's just a few electrical concepts I want to go over. Now, if you already have a basic understanding of electronics, feel free to skip ahead. And if not, let's try and cover some of the basics. So for digital electronics, we use DC current, or for direct current. I should say DC power, direct current. Now, direct current just means that the electric charge always moves in the same direction. So we've got, if we look at a wire, and we've got our electrons with their charges, and we're looking at the flow of this charge. Now, before we can bend these charges to do our bidding, let's look at how we can describe them and what properties they have. So the first is the potential energy per charge. Now, the potential energy per charge we call voltage. Okay, so that's the potential energy per charge. Now, the unit for energy is the joule. And the unit for elementary charges is the coulomb. All right, now, a joule per coulomb we call a volt. And the symbol for volt is a capital V. Next, we want to know how much charge flows per second. Okay, so that's called the current. The current is the flow of charge per second. So if we take our wire and we consider this the cross section, we're looking at how much charge flows per second. All right. Now, the unit again for charge is the coulomb per second. And we call that the ampere, and we shorten that to the amp. And that is represented by the capital A. So the next thing we want to look at is electrical power, and that's the rate at which power is transferred from our electrical circuit. So power, and it's a rate, so it's per second, and it's amount of energy, so it's joules per second. Now, joules per second is also a volt amp, and it's also called a watt. And this is represented by a capital W. Now, the last concept I want to cover right now is called electrical resistance, and that's the resistance to the flow of charge. Now, how easy or hard it is for charge to flow in a material. And that's, the unit is ohm, and the symbol is omega. All right. So now we've got voltage, current, and power, and resistance. Let's look at a simple electric circuit. This is a symbol for a battery, symbol for a resistor, and our current flows in this direction, our conventional current, That's our current flow. This is our resistor, and this is our voltage. And here we've got our positive voltage, and here, by convention, we have 0 volts. So the relationship between your voltage, current, and the resistance is called Ohm's law. Now, Ohm's law says that voltage is equal to the current times the resistance. And if we have any two properties, we can calculate the third. So we can rearrange that so that current is equal to voltage over resistance, or that resistance is equal to voltage over current. Now that's going to do most of the heavy lifting in our calculations. So just one more calculation that follows from the definition of a volt in an amp, and we saw that in a watt. It is that power is equal to I V. Okay? And sometimes we substitute Ohm's law into here, and we get power is equal to I squared R. But it's the same thing. All we've done is substitute the definition of V, IR, in here, and we get I squared R. But it's the same thing. Power is current times voltage. Now, what does that actually mean? Well, power is the rate at which electrical energy is leaving the electrical circuit. And in the case of a resistor, it's leaving as heat. So really what this means is, how hot is my resistor getting? How much energy is my resistor dissipating? And this is going to be important a little bit later. This is just a quick demonstration to show that Ohm's law theory agrees with our experiment. We can see 3 volts, 10 milliamps, and a 300 ohm resistor. All right, so there's 2 circuit analysis tools I want to talk about, and the first one is called Kirchhoff's voltage law. All right, we're going to draw a simple electronic circuit here. Got our battery, 1 resistor, 2 resistor, and there we go. Now, remember our current flows like this. That's I, and the current is the same everywhere in the circuit. This is our total voltage across the battery. And then we've got 1 resistor here and our 2 second resistor here. Now, the voltage law says that the total voltage is equal to the voltage drop across R1 plus the voltage drop across R2. So the total voltage is equal to V1 plus V2. And we learned Ohm's law, which is V equals IR. So we can calculate each of these voltages. V1 is equal to IR1, and V2 is equal to IR2. And that's all there is to it. Just the total voltage is the sum of the voltage drops across the components. I set up 2 resistors in series with a 5-volt supply, and we're measuring the voltage drop across each resistor. You can see that the voltage across resistor 1 plus the voltage drop across resistor 2 equals our 5-volt supply. All right, now we're going to look at Kirchhoff's current law. Let's draw our circuit. Here we've got V. Here we've got 0 volts. This is R1, R2. This is our total current. Here we're going to have I1, the current across R1, or in this branch of the circuit. And here we're going to have I2. And down here, we're going to have I1 plus I2. And the current law basically says that there's continuity of current. So if we start with a certain amount of current here, we're going to end with the same amount of current. So part of that current goes down R1, goes across R1, and part of it goes across R2. So the total current is equal to I1 plus I2. And when you have wires connected together, every wire has the same voltage. So in every branch, we're starting at V, and we're ending at 0 volts. So we have the voltage drop across each resistor is the same. V equals IR. We can rearrange to solve for I. So I is equal to V over R. And I1 is equal to V over R1. And I2 is equal to V over R2. You can see on the power supply, we have 10 milliamps through our single 300 ohm resistor. Here we've added a second 300 ohm resistor, and here we can see that in the second resistor we have 10 milliamps. Added to the 10 milliamps we saw through the first resistor, it gives us a total of 20 milliamps, which we can see on the power supply. Well, that's it for today. Thanks for watching, and next time we're going to start looking at how to control LEDs with a constant voltage circuit. Thanks again, talk to you next time, and don't forget to subscribe and ring that bell. Bye-bye.